Hello and welcome to another episode of Nil Dot Talks. I am Kunal and today we have with us Kaushal. And Kaushal is a very dear friend of mine and we go a long way back. We were schoolmates and Kaushal is a physicist. And Kaushal, would you like to introduce yourself?
Hi, I am Kaushal. So I did my bachelor's and master's in physics, and I specialize in gravity. Currently, I am doing my PhD with Dr. Shailesh Kulkarni at Pune University, and we are again studying gravity. So yeah,
Yeah,
we can go
interesting. Okay, so Kaushal, let me get straight to the question.
Yeah.
The theme of our talks is based on this fascinatingly disturbing thought, which is put forth by Dr. Neil deGrasse Tyson. And he says that if you look at history, the closest relative to the human beings is the chimpanzee. We share around 98, 99% of our DNA with the chimps. So our intelligence stems from that 1% difference in the DNA, like us doing math and science and poetry, and a chimp combining a few things to do sign language lies all in that 1%. So tomorrow, what if we find a life form which is 1% different to us, the way we are to the chimps? How would that life form be like, and what would the encounter look like?
Historically it is not just chimps that are like right now chimps are the closest to humans, but we had other human species as well.
Yeah.
And
The
it would more
Neanderthal man.
the
Yeah.
Neanderthal, Homo erectus, so on. And but I guess it would be sort of how we behave with them. But like human, our species Homo sapiens were slightly smarter than or more reproductively successful than the other hominids. So yeah, it would kind of go the same way where we encountered Neanderthals. So Homo sapiens has actually encountered Neanderthals. We mixed our cultures and so on, but now the Neanderthals are dead. Maybe.
So you say if we encounter a life form, we'll be dead.
No, I think we might get assimilated into them if they are hominids. Of course, if they are not hominids, then again DNA and all won't match.
Yeah.
But if they're just like 99% of the DNA shared with us and then 1% difference, so they will be hominids.
Yeah.
And we would gradually get assimilated into them.
No, but not. Let's just say that they don't share the 99% of our
Okay.
DNA, and they are just 1% more intelligent than us. In the same way we are to the chimps.
Yeah.
How would that life form look like? And if I were to push your imagination a little, what would you come up with as a physicist?
So if they have to come from Earth, they would have to be hominids, and I think we will go there ourselves by genetic engineering or something. If they are aliens, then it's not just about how smarter than they are than us, because they would have their own culture, their own civilization, their own value systems and ethics, and it would be a huge, like there would be a lot of factors that determine how our encounter with them will go.
Yeah. But like, if such a species ends up on Earth, if they are capable of interstellar travel, and if they show up over here, how advanced would their physics be?
If they are capable of interstellar travel, it's going to be really advanced, because you have to reach relativistic velocities to actually travel the stars while you are alive.
Yeah.
And if you are going to get to that point, then yeah, you are like they are going to be, their technology will dwarf ours more than our technology would dwarf the Stone Age man's.
Okay, that's pretty interesting. Okay,
Yeah.
so but like, could we ever, like, if we had to encounter with such a species, do you think we would need a time machine, or do you think physics is capable of? Does physics allow us to build a time machine? Is that a possibility?
From what we know of physics today, no, a time machine is not possible, because we have this idea called causality, which, like, if causality is to be violated, then all of the physics we know is wrong.
Okay.
Yeah, because we have based our assumptions on this.
What is causality? Like,
Yeah, I will explain. Causality means you cannot affect your past, basically. Like, something happens, it can only affect a certain number of events in its future. It cannot affect everything, and it cannot affect its past. So there is a causality means there is a preferred time direction. So if we are talking about relativity,
so time as a linear direction.
If we are talking about relativity, we have this idea of space-time continuum where space and time are merged. But the only difference is space, you can move, like space has like left and right. You can move to the left, you can move to the right.
Yeah.
But for time, there is only like
One
we can
direction,
only move
forward.
forward.
Yeah. So there's no backwards direction to time. But like a few days ago, we were talking about entropy, and if time flew backwards, what would happen then? Do you think aliens would be capable of bending time backwards?
I don't think so. I mean, see, it depends on. Currently, the laws of physics are such that we cannot imagine anything going backwards in time.
Yeah.
And we don't see any, whatever mysteries of physics we have, we are not expecting to find some particle going backwards in time over there. So.
And how about like in Interstellar, they have shown they communicate to the humans through black holes.
Yeah. So the Interstellar gets a lot of things right, and again, it was I think even Kip Thorne said the same thing. So whatever is there outside the black hole, all of that they have tried to get as accurate as possible. Once you are inside the black hole, nobody knows what it's like.
Yeah.
So I mean, their guess is as good as ours.
Yeah.
But then, do you think this alien life form that is 1% better than us will find such ways to talk to us through gravity?
See,
And since your thesis is on
Yeah,
gravitational
so-
waves,
yeah, so again, the only way to talk to us through gravity is by changing space-time in a certain way. And space-time can be changed by anything with a mass. So it's not
Okay.
that. The important thing is you need a lot of mass to change space-time so that we can perceive it. So for example, gravitational waves. The gravitational waves we observe, they come from like binary black hole systems where two black holes are colliding into each other or rotating around each other, or like a black hole and a neutron star. These are like very massive objects, very massive but compact objects. And even then, the gravitational wave magnitude that we get is like 10 to the power minus 17. So such huge objects, you can only detect them at such a small length scale. So yeah, if you want to talk via gravity, you would need a huge amount of mass and energy.
yeah, that's pretty interesting.
Yeah.
And Kaushal, since AstronEra is all about astronomy and you are a physicist, I would like to ask you: is there a connection between physics and astronomy? And if there is a connection, how would you look at it?
Yeah, physics and if you go to any university, physics and astronomy is pretty much the same department.
Yeah.
But
It's not really the same. It should not be the same department, right? Like astronomy is a bit different from theoretical physics.
yeah, astronomy is more about observations of the night sky, while physics is about explaining certain observations that you see. So if you look at the constellations, you look
Yeah.
at the constellations in the sky, they are important from an astronomy point of view because that is how you map the night sky, and if something changes, you know that there's something wrong there.
Right.
They are not that important from a physics point of view because those constellations that we see from Earth, which are near to each other, in space they might be like light years,
Away.
thousands of light years away from each other, and
Yeah.
just we see them in a certain direction, but that's not really relevant to physics. So everything is related to each other because like mathematicians will come and say everything is just math, and then some logician will come and say math is just logic.
Yeah.
Then a philosopher will come and say that logic is just philosophy.
Yeah.
So everything is interconnected in some ways and not that connected because like if you're an astronomer and you would know some science, you would know some physics and all. How do I put this? But when you are the way you conduct research in astronomy might not be the same way you do it in physics. Because in astronomy you are more or less fixated on finding out objects in space and characterizing them and all that, while physics is about how these objects came to be in the first place.
So you're saying there's a difference between physicist and astrophysicist?
There is a slight difference. Even like most astrophysicists nowadays, science has become hugely collaborative. So whatever observations you need, you usually get them from very expensive machines, and a single institution cannot afford it.
Yeah.
So for gravitational waves, for example, we have LIGO, Virgo, this Kagra in Japan, Indigo will come up in India soon. We have this gravitational wave observatories. There are only like 3 or 4 on Earth. There is a proposed plan to send one into space, and it might come up in the next 5 years. But then most of the gravitational wave astronomy as such is about getting data from these machines and then analyzing it.
Right.
So an a gravitational wave astronomer might not even have seen the machine, but he can still do physics with it.
Right. So the machine part is completely different than the theoretical physics part of it.
It is related, of course, because you cannot build a machine to detect gravitational waves if you don't know what are gravitational waves.
Right.
Yeah. So I mean, I'm saying there are physicists who do gravitational wave astronomy, but they have never been to LIGO. Yeah.
What would a physicist do if they encounter this 1% better life form?
We would ask them about their physics. We have a list of questions. What is dark matter? What is dark energy? Do you have a quantum theory of gravity?
Yeah.
And we would see if they have any of those.
Yeah. So this quantum theory of gravity you're talking about, where general relativity meets quantum mechanics and
Yeah.
the hunt for graviton. Can you explain a bit about the graviton? And you were very fascinated with the graviton, so
Yeah, so I don't know how much I can explain because I'm also still studying. I'm a PhD student. I'm not a complete physicist. Graviton is a quantization of the gravitational field. So a graviton is basically like a photon analog. So you have the electromagnetic field, you know, electricity and magnetism, and you also know about photons, you know, single particles of light. A graviton is like that, but for gravity.
right.
Now, the difference between all the other forces and gravity is that electromagnetism or the strong force, weak force, all our theories, like whatever we know of them, they assume a space-time in which these fields are operating, these electromagnetic fields and all. Gravity is the space-time. There is no overlying field.
Yeah.
And so we are trying to quantize space-time now. And yeah, so the graviton itself, I think, I'm not sure, but I think it's because we assume a background space-time and a perturbation to the space-time, like a linear perturbation, and then quantize that. You get a graviton like that. But the direct quantization, as we have done for electromagnetism, fails in the case of gravity because we start getting integrating infinity and so on. So we don't know if it's a problem with math or with.
But do you see it happening in the future, a theory for quantum mechanics and general relativity combined?
Yeah, I think it will happen in the future. I mean, it might not take the form that we imagine it to be, but it has to happen because there are certain questions that. So, if we go back to the Big Bang now, like the initial singularity, at some point the singularity was small enough that quantum effects come into play. Like the Big Bang model right now is completely based on gravity, general relativity.
Yeah.
But at some point you have to account for quantum effects.
Yeah.
Similarly with black hole, we have Hawking radiation, which means the black hole is going to shrink over time.
Yeah.
And at some point it will reach quantum level and you have to account for quantum mechanic effects around that time. So if you don't know how to relate quantum mechanics and general relativity, you don't know what kind of physics is going to happen. So, and something will definitely happen because it's going like, so at that point, some physics will come into play. We'll study it and we'll get some way to relate these two phenomena.
And since you brought the topic of Big Bang, like Big Bang theory is the most widely accepted theory, and like most of the common people out there, they know about the Big Bang, but like you're saying that it's based on general relativity. So is there a model of the universe based on quantum mechanics? Is there a different theory? Like Dr. Jayant Nararikar says that he has the steady state model. So like there are different theories out there. So do you think like
So the thing is, these are all theories of cosmology. Like these are all theories of the largest scale of the universe.
Yeah.
And at the largest scale of the universe, the only important force is gravity. Because suppose you have an electron lying around, it has a negative charge. And electromagnetism, like between positive and negative, is an attractive force. So if there is just a negative charged electron lying around, at some point it's going to the electric field that it generates will attract the positive charge towards it and neutralize it completely. So all the objects that we see, stars, planets, black holes, they are all not charged. They are just massive.
Yeah.
And at large scale, only gravity dominates. So all models of cosmology have to be based around general relativity. We don't see quantum field theoretic effects there yet. Because we are looking at the larger scale.
So you're saying you cannot ignore general relativity when it comes to cosmology. Like it's inseparable.
Yeah, it's inseparable. You need a theory of gravity.
Right.
Yeah, it may not be general relativity. We are like, right now again, the Big Bang model as it is, the currently accepted parameterized form of it is called the lambda CDM model, which is lambda stands for cosmological constant, which gives rise to dark energy. CDM is cold dark matter, so that accounts for the dark matter part of it. And that's the cosmological model which explains the Big Bang up to now. This is just one model. There are some alternative models being proposed even now.
Yeah.
Because we don't know what is dark energy, we don't know what is dark
Yeah.
matter. So some people are trying to make up better models, and maybe they will succeed.
Yeah, but the general relativity is a fact, right? It's based on, it's not just a theory, right? It's a fact.
It's a model. It's like Newtonian mechanics. So
Right.
at our daily life, Newtonian mechanics is a fact. But when you go to the really small or very big scales, Newton mechanics is incomplete.
Right.
You need a modification, which is general relativity or quantum mechanics in one direction. And similarly, general relativity right now, at the scales we are observing it, it seems to be experimentally verified. So it is sort of a fact for the domains we are dealing with.
Yeah, but the fact that we discovered the first black hole a century ago, and now that we have the first image of the black hole, it means that general relativity is a fact, right?
It means that it is a good model.
Right.
But the model can always be made better.
Right.
Something else might come up, like quantum gravity, for example, which combines general relativity and quantum mechanics. That would be a better model. See, if you, again, like suppose, to use an analogy, we have Newtonian mechanics at the daily level. Like if I'm throwing a ball to you, you know how to catch it. Yeah. Newtonian mechanics will help you predict everything about it. But for the atoms within the ball, you have to go to the quantum level. Okay, that does not, like, because the quantum mechanics is a better model than Newtonian mechanics, does not make Newtonian mechanics invalid where it's applicable.
Right.
You can derive Newtonian mechanics from quantum mechanics.
Right.
Similarly, there will be a better model than general relativity. There might be a better model than general relativity. And you can get general relativity as some limit.
Right. That's very interesting, Kaushal. And now that you have explained all these things to us, I have a small surprise for you. And we are moving towards the last section of our video, and it's going to be a rapid fire round. I am going to ask you a few questions, and I'll be giving you 3 options.
Okay.
And you're supposed to select one option. So are you ready for that?
Yeah.
Okay. So the first question, Kaushal. If you had a chance to go on a space expedition, which one of these books would you take with you? A. The Hitchhiker's Guide to the Galaxy by Douglas Adams. B. The Martian by Andy Weir. And C. Cosmos by Carl Sagan.
Hitchhiker's Guide.
Hitchhiker's Guide to the Galaxy. Any specific reason?
Yeah, because it's fun to read. The other 2 books are not that fun to read.
Yeah. So you'll take some humor with you.
Yeah.
Okay, so the second one is, if an alien offers you one of these drinks, which drink would you choose? A. Pan-Galactic Gargle Blaster. B. Butterbeer. C. Soma.
A.
Yeah, because
Yeah.
you're a Douglas fan. Okay. The third question. Which one of these theories would you consider to be the most important one in the world of science? A. General theory of relativity. B. String theory. C. Darwin's theory of evolution.
I would say C. Darwin's theory of evolution, because even though I work in relativity, evolution is like, I don't know how to explain it. Evolution has also been something I dabbled in my college years.
Yeah.
And the theory of evolution does not even make sense right now, because we should just call it the fact of evolution.
Yeah.
It has been observed so many times. We simply, like, it is being observed in labs even today. Even right now, people are observing evolution happen.
Right.
And evolution is more fascinating than the other 2, because evolution actually explains where humans came from.
Right.
Yeah.
Interesting. Okay. If you ever encounter a beautiful alien girl, which one of these options would you choose to do with her? A. Take her on a date. B. Ask you to take her on her planet. C. Learn alien technology from her.
Interesting. I would learn alien technology.
Okay.
Yeah, I can make money selling it here.
Interesting. If you had a chance to meet one of these physicists, who would you meet? A. Nikola Tesla. B. Richard Feynman. C. Robert Oppenheimer.
Feynman. Yeah.
Why?
He was the most interesting of the 3 options here. Like, it depends on your definition of interesting.
Yeah.
But Richard Feynman was actually like a party animal. So
A party animal.
Yeah.
Which one of these animals would you like to have as a pet? A. Schrodinger's cat. B. Laika the dog. C. Ham the chimpanzee.
I don't know who the third one
The
is.
third one is a chimpanzee we sent to space, the first chimp that we
Okay,
sent to
okay.
space.
Yeah. I would go with Schrodinger's
Schrodinger's
cat. Yeah,
cat.
because I like cats.
Okay, you're a cat person. Anyway, so this is the last question, Kaushal, and this is not just for you, this is for everyone. If you had a chance to meet Dr. Tyson, what would you say to him? A. Travel to AstronEra's office to do a Nil Dot Talk. B. Get AstronEra people to come wherever you are to do a Nil Dot Talk. And C. Do a Nil Dot Talk with AstronEra people over a video call.
I think A.
A.
Sounds good.
Travel to AstronEra's office to do a Nil Dot Talk. Interesting.
Yeah, it will be fun to see him here.
Yeah. Anyway, Kaushal, it was such a pleasure to have you over here, and this is the last section of our video, and we end it over here. So, guys, keep watching Nil Dot Talks. Thank you for being here, and clear skies.